This is not possible.
I know I watched it a few weeks ago, maybe a month ago or something, but I had a calculator, a scientific calculator, and I'm not sure if I left it.
I think there was one in lab.
Okay.
You want to check in there now? The door's open.
Okay, thank you. Yeah.
Yeah, because I haven't.
I
Yeah.
checked right before spring break. I was like, where did this go?
Oh gosh.
And I don't know, it could have been missing longer than that. I'm not sure.
Yeah, I'm so sorry. I have not seen it.
Okay. But you said there was
Okay.
one in lab?
Yeah, there is one in. I think there's one in the lab, so you can check in there. Yeah, of
Thank you.
course. Okay, so let's see. I've got to share a screen here. What screen shall I share? Let me make some notes. Can you guys hear me okay? Van, Mina?
Yes.
Yay, thank you.
Yes, sir.
Yay, thank you.
You're welcome.
Let's see. Good morning, Diane. How are you? Let's see here. Good morning, Cynthia. How are you?
Good morning.
So your background is odd today. Does that look like Santa Cruz, like a webcam from Santa Cruz or
San
something?
Diego,
Oh, I got it.
taken from the
Huh.
Museum
Yeah,
of
it's,
Man Tower, overlooking Balboa
oh my
Park.
gosh. Oh, no kidding. Balboa Park. Right. I've been there. I've been to Balboa Park. And I remember thinking, who's Balboa? Like I heard about him in elementary school, but that was the last I heard about him. I don't remember. He like did a lot of sailing somewhere.
Something like that, yeah.
Something like that. Oh God. Nicholas,
Good morning.
do you remember who Balboa was?
No,
Oh, come on. You're like the smartest guy here. You've got to
I'm
remember.
sorry.
Does anybody remember who Balboa was? Does it matter who Balboa was? I don't know. He has a park. We should remember him, right? Oh, God. Brandon, good morning.
Good morning.
Do you remember who Balboa was? You know, Balboa,
What, like Rocky
the guy
Balboa?
with the... No, not Rocky Balboa. Not Rocky Balboa. You know Balboa, the Spanish
Oh
conquistador?
God, no. Sorry, I'm not that into history. It's not my subject.
Evidently. Oh my God. Okay, I'm going to look up Balboa.
Isn't it like
on-
Gaspar de Balboa or something like that?
I don't know. There's Vasco Nunez de Balboa, Spanish explorer. This is in Britannica.com. Yeah. Balboa Park. There's a Wikipedia page.
Of course there is.
Vasco. Yes, of course. Oh, he settled in Colombia. Oh my God. I should remember this. Okay, hold on. I've got to share this with y'all. I've got to make this bigger here. Okay. Let's share a screen. This is Vasco Nunez de Balboa. He is best known for having crossed the Isthmus of Panama to the Pacific Ocean in 1513. And he looks kind of like a nice guy, according to the painting, right? Doesn't mean he couldn't be a complete bastard, I'm sure. But, and then he was the first European to reach the Pacific from the New World because he went across Panama. Took like 100-mile march or something like that, or a 40-mile march. There's his signature. Isn't that wild? Can you imagine having a signature that complex? I'm not sure I could reproduce it. Okay. All right, enough Balboa stuff. What else are we going to do today? So just so you know, here's our home page, right? I don't know how yours looks, guys. I'm sorry. This is how mine looks, right? And I added something to assignments, which are notes on chapter 20. And this is just PDFs of some of my notes. And I have more, and I'll add them. But it's basically homework stuff. And then to files, I added a bunch of stuff. I think these are updated now. We go to Files, Lab, then you can go to Crystal. I think everybody's done that. Then Raman, I think everybody's done that. Now I have rhodamine 6G, and we've got all of your rhodamine data there. And there should be like 2 files per group, one with the fluorescence and one with the UV vis, so you're gonna have to take them both, right? And finally, we have the HPLC, and we have results for the following groups of 3 or 4 possibly people. For example, Casey, here's her results. And we can, well, actually, tell you what I'll do. I'll go over and I'll show you what they look like.
That's not me. That's the other Casey.
That's the other Casey? How dare he or she? I'm sorry.
C.
Casey, is Casey always a she?
No.
No,
No, I
Casey's
don't
very
think
gender
so.
neutral.
That's a very gender neutral name. My brother is named
When I was
Dana.
a kid, it was more masculine than feminine. I think it's in that shift.
I know. It makes for a sort of a buff girl, sort of a macho girl.
I'm not tough.
You're not macho?
No, I'm not tough. No.
Oh, poor Casey. Oh my God. Okay. So here's what the HPLC printout reports look like. And I'm going to make this just a teensy bit smaller now so that we can see more of it. When I make it so small though, the peaks, the lines disappear. It's like, gosh darn it. That sucks. But here, for example, is a somehow this was done by Mr. Student and by his student. But I have a feeling it was probably Fook, since Fook's data is here. And Fook is not here today.
I'm here.
Right, Fook? You're not here?
No,
Oh, you are
I'm
here!
I'm just
You have
listening.
been. How come I didn't see you? You're
It's just
hiding.
that no, it's just that you were talking, so I didn't want to interrupt in the beginning. When I
No,
came here.
no, you were hiding. I think you were hiding.
Well, Fook's just very nice.
Do you think? No, he's not nice. No way. You're not nice, are you, Fook?
I'm not sure. That's other people to judge.
Oh, damn it. Damn it. He's so nice.
He's the nicest person in the class.
Oh my God. You've out-niced me, Fook. Curse you. Okay, shut up, Roger. This is how it's going to go today because I am so tired. I can't even think. But so here's an HPLC printout, right? And this is P2A2, right? And this sample name is 40 ppm, right? Now, it's really lucky that we have a little bit of information, like in the name, to identify this one as a 40 ppm standard, even though it's not exactly 40 ppm, it's somewhere around there. And in this report, we have essentially 3 peaks, right? We've got this one little guy here at 0.99 and 1 point whatever minutes here. And this first one is right, let's call this 1 minute, this first peak, right? We've got a 1 minute, a 1.5 minutes, right? 1.475 exactly, and then 4.294. So it's funny that these look like histograms, isn't it? That these look like the probability of making an observation versus the observation. And that's because that's exactly what they are. Exactly. Isn't that cool? Now you'll notice here that there are 4 significant figures in the identification of lambda max here, right? And I want you to ask yourself, does this level of certainty in defining the peak, the sides, the peak, the other side, the tails, does that amount of accuracy justify all 4 sig figs here? And I think it very well might. I think it very well might, It's like, can we say with 95% confidence that the peak of this peak, the top of this peak, the mu value for this Gaussian-like peak, is that at 4.294? And I think the answer is yes. I think it's yes, definitely. So, so question is, what are all these 3 peaks and why are there 2 copies, right? Who can tell me why there are 2 copies? One at sig equals 250, one at sig equals 270. Does anybody know the answer to that? And is willing to say it out loud? Fook, do you know?
What's exactly is the question, Dr. T?
Yeah, I know. What's the question?
I just don't
my
understand
God,
the
Fook.
question. I just don't know the question.
I know, but it's such a clear question. My God.
May you please repeat it
I don't
again?
like to be I don't like to be out niced, Fook.
Okay. Sorry.
You have to be meaner.
No. No.
No, you're not going to be meaner. Please.
No.
I want to be the nicest person here. You guys all have to be mean.
No, meaning
Please.
does not do good on my mind. No.
Oh, come on. The world needs meanies.
No.
We gotta have meanies.
No.
Please, Fook.
No.
Oh, come on. Oh. All right. Okay, I'll be the meanie.
No, you're not.
So, question. Shut up. I'm being mean. The question is, why is there a 250 and a 270? What's going on? Why are there 2 almost identical looking chromatograms? Nicholas, come on, you know.
I'm not an HPLC expert. I haven't done this experiment. I don't know off the top of my head.
Okay, all right, I give up. So, so we simply recorded the absorbance at 2 different wavelengths.
I can
right?
try, Dr. G, maybe.
I already gave the
Oh,
answer.
oh, really?
I just gave the
Oh,
answer.
never mind. Wait, you didn't.
Damn it. I did. I said we recorded it at 2 wavelengths.
Oh, yes.
How is that not an answer?
Never mind. I was gonna say something
Come on, Pook.
smaller, but not the same.
Oh, I
Not the
see.
same
Now
though.
you were
It
going to say
wasn't
something
right. It
similar.
wasn't right.
Oh, yeah. Oh, yeah. Oh, of course you were.
No, it
You
wasn't
were going to
right.
say exactly what I said, right?
No, my answer wasn't right.
Oh, my gosh.
My answer's not gonna
Oh,
be right though.
who's Mr. Nice Guy now?
Don't-
I'm just joking around, Pook. I love you. I love you so much.
But yeah, it's not the
I'm
right
just
answer
messing
though.
around.
It's the same, but it's not
All
up
right.
near the
All
answer that you give.
Oh, come on. Don't give up so easily. So we recorded at 2 different wavelengths. So why are there different size? Let's focus on this peak here at 4.29. It's real large here. Well, it's like 25. And it's smaller here. It's larger here than it is here. It's larger at 250 than it is at 270. Does that make sense?
Well, we were measuring two different things, the benzoic acid and the caffeine. So it wasn't like
Exactly.
one wavelength kind of favoring, each wavelength favored each different analyte.
Perfect. Perfect, Cindy. I love it. So, yes, that is actually true. So now let's look at peak number 1, 1.475 minutes. That is at 270 nanometers. It's like 150 MAUs tall. And at 250, it's 14, it's like 60 MAUs tall. Sorry. So it's 150 versus 60, right? So it's 3 times taller at 270 than at 250. Now, if we come over here, we see this guy is, gosh, it's almost the same. Looks like maybe 25 and maybe 20. So this guy here is a little smaller at 270 than at 250, right? So we can use this information in the spectra of, I'm sorry, I don't have the spectra right offhand, but you can tell that at 270 here, oops, at 270, the caffeine has a peak. It's kind of like, it's a second peak. There's 2 peaks, and one at 250, one at 270, and the 270 peak is larger in caffeine than the 250. So that helps us to distinguish them. Okay, another quiz. Casey, this is for you. This is for you. Why is this first peak skinnier than this second peak? Skinny peak, broad peak. Skinny peak, broad peak. Why might that be?
I don't know. It's not because there's more. I know that.
Right. That's not, yeah. It's like, that's a good point, because, you know, as the thing grows, it appears to get wider. But if you actually measure the width at half the peak, that should be at the full width at half max. That should be invariant to the peak height, I think. So it's not the size of the peak, it's not the height. But you will notice in general that things that take longer to elute, the longer the elution time, the broader the peak.
That makes sense.
Yeah, because there's more time on column for it to get scrambled up a little bit. See, isn't Casey smart? She's so smart.
I just told you what it was.
Darn it.
And then you told me what it was.
Oh, I can't account for my habits as a teacher. I just want everybody to know that Casey is super smart.
We knew that.
Okay, so I know. I'm just okay. Let's see here. So we've got peak and peak, and we've identified more or less that this first peak ought to be caffeine, and the second peak ought to be benzoic acid, right? Now we must commit to memory the two numbers, 1.475. What did I just say? 1.475. And what's the other number? Brandon?
4.294.
Excellent. Excellent. Good. I overreact. I'm sorry. I don't mean to sound like a manic, crazy person, even though I am one.
It's okay. We all know how crazy you are. Just keep going.
Yay. Okay, good. I'll keep going. So signal equals 250, 1.475 here, and the only other number that we care about is this number here, 155.915, right? 4.294 is 107 here, right? Now, you can tell here that between 250 and 270, the 1.475 peak here increases in area from 155 to 457, right? So that means that this peak is very likely caffeine, right? So if we were to say, okay, let's assume that this peak is caffeine, and we're going to assign a point on the calibration plot to the value of 40 parts per million, adjusted to an exact value, and an area of 155. All right. That means that we'll take a spreadsheet and we'll record those two values, and that'll be 1 point on our calibration curve. Yeah. Then what we're going to do is we're going to go over here, and we will get. Oh, this is Diet Coke here, so let's go over here. So now we're going to go over here, and we're going to get 60 parts per million, right? Then for 60, what we're going to do is we're going to take the 1.463 peak, right? The first of the two. And we're going to take the value 238, 0.57785, whatever, lots of sig figs there, but, right? And that'll be the second point on our calibration curve. So if I've done this correct, I took them both from 250 nanometers, right? So here's 60, here's 30, and this must be 15 over here. No, 20, this is 20, right? And then here's 250 and 20. Oh, and this one looks pretty screwed up here, actually. But we could take this guy here and throw it on there. And then this guy here would be like 98, right? We probably want to reintegrate this peak because the baseline is messed up. But we could integrate that peak. And the thing to do here is when you go and you make the calibration curve, there's really two things to keep your eye on. One is to use the same wavelength. Like if you use 250 to start with, just keep using 250. Or if you use 270, just keep using 270. Right? If you want to quantify caffeine, you got to use 250 nanometers. So you take this peak, and then that means you come down here, you go to 250, and you take this peak, and you're going to take this area. Right? So hopefully that helps like your later analysis of the data, right? And then you'll build up a calibration curve with these guys, and there's actually a decent discussion of this. I think it's in the lab manual. Here it is, in the lab manual. And what you can do when it loads, it'll load, is you can come down to here's the table of contents, right? And this is the rubric that I have. And I'm planning on making the format even shorter this semester, right? So we're only going to do the data analysis, right? So most of the rubric won't count. So I'll go down to data analysis here. And I'm actually going to come, well, I'll just go there, page 73. Oh, come on now. Okay, so I'm going to open this guy up in Acrobat. Hold on. Okay. Okie dokie, so now I'll go to share. There we go. Okay, so here's the instrumental analysis from spring 20. We can go to guide to data analysis on page 73. And the first thing to do is to plot the calibration data in Excel, right? So we will see what that looks like here down below, right? And what that's going to look like is a series of parts per million, and then a series of signals, right? And in the case of the HPLC, you won't have a 0, but you'll have 3 data points here, like 15, 30, and 60, or 10, 20, and 40 or something. And then for each of them, you'll have a signal. And the signal that I would prefer that you use is the area. So for the signal here, you're going to use the area. Oops, sorry, just the area, right? So let's see here. And more particularly for caffeine, you'll use, for example, that area, right? And this is just taking 250 as an arbitrary choice. You could also use 1.475, and you could also use this area here, right? You could also use that one. Oops. But I would prefer you not. I would prefer just you pick one and go with that. Okay. So now we go back to the lab menu and you'll have this, the parts per million, you want to correct them to be as accurate as you can. So you want to go back to how much you weighed and what mass or volume of water you used or whatever. And you'll have to do those guys there. And then you're going to linest these data. And then you'll do the calculations according to this. And this is a black box right here. This is a, I don't know how they got this, but this is some statistical magic that they did in order to propagate the uncertainty in this calibration curve into an uncertainty in concentration, right? So where you take these calibration data, then this level up here, the signal level, and see where it intersects that calibration line, and come down to this x-axis here, get a concentration. Then when you want the uncertainty in that concentration value, S sub C, then you've got to take a bunch of data from the calibration curve, and you've got to aggregate it into SC, and you've got to work on it there. So we will cross this bridge again, but I just kind of wanted to get you prepped in case you want to make the calibration curve. And if you want to send me, like if you're super smart, kind of like maybe Casey or something like that, then you will send me, yes, then you will send me your data and say, hey, Dr. T, does this look right? And you will send it to me in advance of the due date, right? You won't just like wait until the due date and then send it to me, right? Excellent. I like it. I know Cindy's going to do it. I know Fook is going to do it like the day before it's due, but he will do it, right? But I prefer, Fook, that you send it to me like 2 weeks before it's due, so I can actually have time to get back to you. Okay?
Yes, sir.
Oh, he's so quiet. You know I love you, Fook, right?
Yes.
I just like to give you a hard time for some reason. I don't even know why. I don't know why. I don't know why. Maybe it's because we're similar.
Yeah.
Okay, all right, buddy. Okay, so now let's see here. So that's all I want to say about HPLC right now. We're starting to get the data. They're starting to trickle in, so I thought I would say something about this. So let me go all the way over to PowerPoint here. Right, and let's talk a little bit about our program here. And let's talk first about semiconductor detectors. And this is actually part of a general subject area that I think is pretty darn interesting. And this is about basically what is a diode? You know, how do diodes work and what are they? And I think it's a little bit of criminal to let you guys go throughout your lives with a chemistry degree not really knowing the intricacies of how a diode works. Because, you know, if you know how a diode works, you can understand a transistor, and then, you know, that's basically the single most sophisticated, you know, semiconductor thing, you know, sort of sub device that you can make. So, you know, the rest of them are all just variations on the transistor. So let's try to understand a diode here. And I think it's fair to start that conversation with a conversation about silicon. And let me just try to think here how to do this correctly. Actually, let me use my stupid camera here. But silicon is a pure crystal, right? And it's a pure crystal of, has the diamond lattice. And when you talk about this diamond lattice, you can just flatten it out, kind of like that, right? And so every intersection here is a silicon atom, right? And when you think about this as basically just a big extended molecule, right? Then you can think of it as that they're in this big molecule, there's MOs, there's molecular orbitals. Right? And the orbitals come in two varieties. They come in antibonding and bonding orbitals, And the difference is that for every antibonding state that you populate, you create a little more repulsion between the atoms. And for every bonding state that you occupy, you create a little more attractive force between the molecules. So that's really the difference. So when you, with pure silicon, there's a lot of almost purely atomic orbitals, like the 1s and the 2s and the 2p. Those shells are all closed, and so they don't contribute much to bonding. But the 3s and 3p, there's 4 electrons there, right? And those 4 electrons, they contribute to the bonding or anti-bonding qualities of the silicon crystal, right? And it just so happens that, for Si, then that makes 4 bonds. That means that 4 bonding molecular orbitals are filled and no anti-bonding molecular orbitals are filled. So, so you can say then in Si infinity, for this crystal, right? It's a crystal molecule. That it has essentially infinity bonding MOs and infinity anti-bonding MOs. Right? Now, each silicon atom has 4 valence electrons, right? Right? And each silicon atom makes 4 bonds. So that means that every silicon shares a an MO with a neighboring silicon atom, right? So that means that what can we say about the bonding MOs in a silicon crystal? Are they filled or are they unfilled? Let's take a poll here. Diodes are cool. I love it. Okay, so Jonathan says diodes are cool. Now, how many of y'all believe that that silicon has filled states or empty MOs? How many believe that they're filled and how many believe they're empty? And we're talking about the bonding MOs. Taryn thinks filled. Filled. Good. Fuchs says filled. Excellent. 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 Okay, good. So now there's a landslide, and the landslide is correct. And the landslide says that the bonding MOs are all filled. So basically, what we have here is a series of spin paired electrons here, right? It's filled, and in addition to that, all the electrons are spin paired. Right? Which is an interesting thing, right? Because that means it should be slightly diamagnetic in character. And that may or may not be true. I don't really know. I've heard that. So, excellent, excellent. So now how about the anti-bonding MOs? Let's talk about the anti-bonding MOs. Are they empty or filled?
I think
Empty,
anti-bonding.
exactly.
Anti-bonding.
No, anti-bonding are empty.
Yeah.
Because empty, right? Yeah, good, excellent. So, so now, yeah, so these are all empty, right? It's just because, it's like say difluorine or dichlorine, right? There's just enough, there's no antibonds, right? There's no population of antibonding orbitals in those goes. There's just one bonding MO, and so like silicon, it makes bonds to four neighbors, four bonds possible per, and so that's perfectly filled, right? So that's, that accounts for the fact that silicon is a very high melting solid, it has a strong bonding character. It's, it's a little bit brittle, but it's a fairly tough material, Well, I guess that's opposite, right? It's brittle, but it's strong, shall we say. So so when you have silicon that's all spin paired in the bonding orbitals and all empty, there's no electrons at all. That means that this state here will be electrically insulating. Right? Because, and it's interesting to think, I used to puzzle over this a lot, you know, and it has to do a little bit with the contacts. And it's possible to get some charge into pure silicon with the right contacts. But with normal contacts, with normal work function contacts, silicon is insulating. And the reason that it's insulating is that the Pauli exclusion principle prevents the motion of charge. In order for charge to move in pure silicon, there either has to be an electron in an antibonding state or a hole in the bonding states. Does that make sense? Please say yes.
Yes. Yes.
Okay. Thank you, Fook. Now, I want Nicholas Robineau to say, yes, Dr. T, that makes perfect sense. Can you say that, Nick?
Yes, Dr. T, that makes perfect sense.
All right. I've got it. I'm a perfect teacher. I taught everybody. I'm just kidding. Sorry. I get a little overexcited. This is me today. I am like, ooh. I don't know why. But Cindy, does it sort of make sense to you? Why the Pauli exclusion principle would be related to conductivity in a material?
I haven't thought of it before, but yeah, okay, it makes sense.
Okay, well, that's good. I feel humored, but I'm not sure if I believe you. So why would, the Pauli exclusion principle states that there can only be one electron with all the same quantum numbers in a given atom.
Right.
Yeah. So, that includes spin, right? So then if you have, if you've got all the same quantum numbers, S, there's N, L, M sub L, and M sub S, right? These are like the good quantum numbers for atoms, right? And if you put them into a molecule, I don't know, you still got the same number, I think. And the last one is M sub S. And so you can't transfer another electron with the same quantum numbers into another atom, right? That violates PEP.
Right.
And it basically says you just can't do that. And if you do that, the world will explode. So we don't want the world to explode. So we're going to instead say that at that energy, right, in that energy state, that N value has to be higher. So you could promote that electron to a new N value and then transfer it over.
Yeah.
Right? Good, excellent. So now what that means here is that if you can promote this electron up in energy to a new state up here, then you can,
then you can anti-bonding.
Right, exactly. Now, I'm going to explain to you why material scientists use electron volts and not fucking joules, which are annoying. Because this gap here for silicon is about 1.5 electron volts. I don't know, 1.5, 2, maybe something like that. It's like low volts, right? More than 1, less than 10, less than 4 for sure. So let's say this is 1.5 EV here. This is actually called, in chemistry, we call this the HOMO-LUMO gap. In material science, we call it the band gap. And that's what, the band gap is what makes a semiconductor. I'm trying to think of something funny to say, like an old crotchety British guy would say, like, it keeps everything from going to heck, keeps everything from going to bollocks or something weird like that, But it's really, it kind of creates some order in these materials, right? So it makes silicon insulating, right? Now, it's also true at room temperature that some of the electrons can be thermally excited across even a large barrier like 1.5 volts. At room temperature, there will be a small, maybe one in a billion or so electrons will have been sort of sloshed up together, and that one electron will get promoted up. So there is a small amount of conductivity in intrinsic silicon at room temperature, which goes away quickly as you cool it. Does that make sense? Thank you so much. I'm asking you guys to do a lot of thinking right now, but it's okay. So now, in order to understand a diode, what I'd like you to understand here is the effect of substitution on a silicon crystal. It's called doping. And to explain doping, I've brought along one of my favorite athletes, Mr. Lance Armstrong. And only Cynthia gets it, I know, because poor Lance has been forgotten
My
by
husband's
history.
a big Armstrong fan.
Oh, I am a big Armstrong fan. That guy, he wasn't the only guy doping. Everybody was doping, but everybody hated him because he was winning.
They all stood in a circle and pointed to each other and said, I had to do it because he was doing it.
Right. Exactly. Yeah. And there was this one of his domestiques was a Mennonite. He was either Mennonite or anyway, but I think he was Mennonite. And these guys are just known for their integrity. And what happened with him was just like such a crazy meltdown, right? He must have felt so guilty because he was doping, right? That he pointed the finger first at Armstrong, and then he was forced to admit that he was doping too. And it's like, oh God, come on. But anyway, so doping is not like doping with Lance Armstrong. So I'm going to say Lance is not what we're talking about. What we're talking about is a substitution of, for example, a nitrogen for a silicon atom, or you could say phosphorus or whatever, right? And let's take a look at two random nitrogen and silicon atoms floating through the universe, minding their own damn business. Here's Mr. Silicon, and here's Mr. Nitrogen. And these guys are completely content as atoms, right? But Mr. Nitrogen is different than Mr. Silicon, right? Because Mr. Nitrogen has, atomic number of 7, which means, don't be like Lance. Dylan, are you a cyclist maybe?
No.
Okay, but you know about Lance somehow.
Yes.
Okay, cool. Yeah, I'm an unbelievably out of shape cyclist. Like I can ride around the block now. I'm back to like 3rd grade. But but I was a big Lance. I was so crushed when all this came down. I was just crushed. Anyway, I even bought the book. I even bought his book and I read it. I read the whole thing. And he told the story of how he had testicular cancer and how fucking French company that was sponsoring him dumped him mid treatment. They're like, no, you cannot perform. You are not for us. Puh. Right? And then there was the American company that makes the cool sunglasses. I forget their name now. Not Gecko, but anyway, something like that. They picked him up and they told their insurance company, either you cover this guy or we're going to pull everybody in our company from your insurance company. So they leveraged this insurance company to pay for Lance, and they got it done. Otherwise, the guy would be dead. So anyway, Mr. Silicon and Mr. Nitrogen here, they meet in a dark alley and they make a few bonds, whatever. And then eventually the universe rains down a whole bunch of silicon and a bunch of heat on them. And now you have a crystal, a tetrahedral crystal with a nitrogen atom in it. Oops, let me see here. Right, now you have a substitutionally screwed up silicon crystal, right? We got silicon, 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 nitrogen, right? And now what is this nitrogen going to do with a 5th electron when it's substituted into a silicon crystal? Well, I will tell you what that nitrogen is going to do. It is going to pretend that it, well, yes, but you see, there are hidden things at parties. And
Okay.
this nitrogen will hide his identity, right? This is like a Nazi party, right? Where you can't be yourself. You have to be a Nazi. I'm sorry, Casey. It's true. This is the way nature works. Yes, yes, yes. This is how it's done in nature. If you are substitutionally doping, you hide your identity and you ditch that extra electron. You ditch it. You say, I don't see no electrons here. And then the other silicon atoms are going to be pacing around you saying, is that a positive charge I smell? Yes, we are supposed to lie now. Get used to it. I'm making a metaphor so you understand substitutional doping,
You
right?
could have chose a different metaphor.
But you wouldn't remember. Lie and dope. No, dope and lie.
Right. Gotta get the order right.
Yeah, you got to get the order right. Dope and then lie, right? Dope and lie. So what happens is the silicon will literally, I mean, the nitrogen will literally lose that electron. Yes, Brandon, I have to traumatize you. That is actually true. Yes, you do. Yes, dope and lie. Dope and lie, right? So when the nitrogen goes into the silicon crystal, it behaves like a silicon atom, and it makes 4 bonds. But there is an extra electron. And what happens to that extra electron is that the price being paid for those 4 bonds is enough to put that extra electron into the conduction band, into the antibonding MOs, right? Yeah. So now what you have, let me make it here. So now you have nitrogen. This nitrogen now becomes plus. Shit, I drew over the N. Oh well. N plus, right? And then what this looks like in the MO diagram is is you have one electron in the antibonding orbitals, and you have one hole in the bonding electrons. So this is a negatively charged electron in the conduction band, and this is the valence band, and this is not mobile, but this son of a bitch is mobile. This is N doped Si. So we are very close. We are very, very close to a really important cognitive breakthrough for your whole friggin' life, okay? The next part of this is to imagine the same situation but with a boron substitution. Now, boron has 3 valence electrons, right? Nitrogen is a conformist, right? Is that a bad thing? Or is that just nature? I think that's just nature. Boron is also a conformist. He's a conformist. Right? He's also a thief. Boron. He's a conformist and a thief. Can you believe that?
If he wants to fit in, he's going to have to steal an electron from somebody.
He is. He does not care. He's kind of like, oh God, don't say it, Roger. Okay. No, 0 references to contemporary politics will leave my lips ever unless I slip. Okay? So, this guy is also a thief. Oh, it kills me to do this. But anyways, I'm gonna keep my tongue. I'm gonna keep my tongue shut. And that boron is gonna steal an electron. And now it will make 4 bonds. Right? And this is now going to have the following picture. Now this is going to have a negative charge that's not mobile. And this is going to be the boron atom. And this is going to be the nitrogen atom. Right? But it's also going to have a hole which is mobile. Okay. Now that mobile hole now, how many of you are trying to keep in your mind the difference between a hole and a missing electron? Right? This boron atom stole an electron, shoved it into its core, pocketed it, stole it from the valence electron content of that silicon crystal.
The electron's not missing, it's just misplaced.
Misplaced in someone's pocket.
It'll turn up.
It'll turn up. Actually, this guy, I think it's pretty much stuck there. But it leaves but it leaves behind a hole, you know, it leaves behind a hole in the lattice. And that hole can move. How can a hole move, Casey?
Shuffling of electrons.
Exactly right. Exactly right. There's this hole in the valence bond made to boron, and a neighboring electron says, hey, there's a hole here. What am I going to do? So it goes and fills the hole, but then it leaves a hole where it was. And then another neighboring electron says, hey, there's a hole here. So it fills it and leaves a hole where it was. And now the hole has bounced twice. Right? That's the same idea as there's a whole class of particles. And the most famous one right now is called the Majorana fermion. You'll see reference to it in the popular literature, but it's a quasi-particle, right? Because it's not itself, it's not really a particle. It's the absence of a particle in an otherwise complete lattice, right? So a hole is a quasi-particle. And so this quasi-particle can move throughout the lattice, yeah? So now imagine, if you will, a junction between P and N-type silicon, right? Now you've got N-type Si and P-type Si, right? P-type Si, now here I'm using N. This is not nitrogen. It's any group 5 element, right? So it could be nitrogen or phosphorus or arsenic. You know, practically probably it's limited to those 3. But it's any electron with 5, or any element with 5 valence electrons, you know? And this is This is boron, aluminum, germanium, boron, aluminum. The fuck is below aluminum? I forgot. Who knows what's below aluminum? Somebody's got to know. Boron, aluminum, phosphorus, silicon.
I can search it up. What type of element is it? Non-metal or non-metal,
Just
sir?
it's a period. It just need the periodic table. Here.
Like gallium or something weird like that.
Yeah. Hold on.
How do you spell
I'm embarrassed.
Bologna? I'll search it up for you, sir. Hold on.
No, don't search it. It's done. Here. Hold on. It is gallium, right? Boron, aluminum, gallium, or nitrogen, phosphorus, arsenic.
Yep, that's true.
Boron, aluminum, gallium, and nitrogen, phosphorus, or arsenic. These make N-type, these make P-type. Plus, you'll also notice that sorry, this got off scale here. That you can also, this is for a group 4 semiconductor. And a group 4 plus a group 5 is N-type. And a group 4 plus a group 3 is P-type. But anyhow, let's say we place an N-type and a P-type semiconductor together. What will happen is that, you know, the electrons from the N-type will fill the holes from the P-type. And these guys will annihilate. And or if you're a Dalek, they exterminate. Okay. So did nobody get the Dalek reference?
Oh,
Yes, they mug each other for electrons. It's like, oh, give me your electrons. But actually, you know, for the N-type, it's like, what electron? I have no electrons. What is that electron out there? I don't know. That's not my electron. But you're positive? Yes, I'm positive. Said the cation, right? Thank you, Fook. That was funny. Are you a cation? Yes, I'm positive. Thank you, Fook. I got another. Now Terrence crying and laughing. Good. Excellent. I love it. Okay. So what happens then is this makes a depletion region. So you have you got an N-type and a P-type. Oops. And this is called the depletion region. Or the PN junction. Right? And it actually has a fairly strong electric field. And I'm going to show you briefly where it gets that electric field. Okay. I'm going to try to do this. And it gets this electric field from the leftover nuclei, the guilty parties, right? You know how when a dopant goes to a party, like let's say you're a boron atom and you want to go to a silicon party, right? You're going to go there and you're going to steal an electron and you're going to pretend to be a silicon atom, right? That's what I would do. Right, Casey? I think that's
Sure.
what, I think that, okay, cool. So I steal an electron, I pretend to be silicon. And now that means that now I'm hanging out here and I'm a B minus. I'm a B minus here. That's his boron, right? But I'm not mobile, I'm stuck. And then there's a group 5 element here. Say I'm phosphorus plus, right? And I'm phosphorus plus. And I'm stuck. Now this phosphorus boron pair, this makes an electric field in this direction, right? From left to right. And this depletion region now insulates and rectifies. Okay, I am done in literally 30 seconds. I will be done. I lost Casey. Cindy's hanging on by a thread. She's hanging in there. I got 30 seconds to go. And to close off this important part of your education now, if this slab, if this PN junction is in a circuit, it behaves as a diode. Oh, that's so cute, the kitty.
Sorry, she wanted up in the window.
I love it.
But
I want in the window too.
Hi,
I want to sit in the window.
Isabella.
You have a cat, Casey?
yes.
Oh, I didn't know that.
That's cool, huh? I know. I'm jealous. So now if you make this side of the electric field positive, the positive terminal, and this side the negative terminal, then you drive holes and electrons together, and this conducts. If you make this side negative and this side positive, you pull them apart and this insulates. And now you have an asymmetric, you have an asymmetry, right? Right? So now you have an asymmetry. I have to traumatize you a little bit so you learn better. Oh God. Okay. So I'm afraid that's true. But does that make sense? That there's that the depletion region insulates and rectifies. And by rectifies, it means under forward bias. It conducts, and under reverse bias, it insulates. Okay, I'm done. I'm 3 minutes over. I'm sorry. Sue me.
Professor, can you move
Call the-
a little bit, please?
Like that?
Yes, please. Thank you.
Okay. All right. Any questions? Cheeky comments? Perhaps? No cheeky comments? I think deep down I'm kind of a mean person. That's why people don't talk. Maybe, I don't know. I don't know. Oh, Taryn says no. Okay, all right. I'm not trying to be mean. It just comes naturally. Okay, all right. So I better hang up now, guys, because I'm not supposed to go over. And I am available today between 12:30 and 1:30, and if you need me, just contact me by email, and I will be there. I promise. Bye bye.